Hello and welcome to the training module on fundamentals and technical insights of renewable energy communities. This training section will focus on the technical aspects of photovoltaic plant design and installation. This video is created within the framework of the EnerCmed project, which aims to foster the energy transition in energy-poor Netherlands by developing renewable energy communities integrated with nature-based solutions for urban island mitigation. As already mentioned, in this training section, we will deal with the PV plant design and installation, defining the optimal PV panel positioning, including inclination, orientation, and shading, energy production based on the geographical location, maintenance and operation conditions for long-term efficiency of energy systems. An optimal plant design coupled with the installation verifications maximizes the energy production, ensures safety and compliance with regulatory standards and area restrictions. This enables the renewable energy communities to effectively deliver its environmental, economic, and social benefits. To better treat this topic, the following chapters will be analyzed. Before starting the PV plant design, a deep analysis of all the norms related to the PV plants must be performed. In this slide is presented the national regulatory framework for Italy, starting from the one which promotes the use of renewable energy sources, the other which introduced simplifications for installing solar systems, types of the necessary permits, up to the norms for the requirements for grid-connected systems and mandatory security devices to be used. Based on the typology of the plant, its positioning, power installed, area restrictions, or modification of the building structures, according to the Italian building code, different authorization procedures are required, such as the ones presented in this slide. Before dimensioning the PV plant, the first step is defining its position and gathering some information regarding to the geographical area, so topography, surface composition of the nearby area, building or terrain characteristics as the area composition, abstractions, albedo of the components, and the weather data referring to the solar radiation, to the wind speed, to the precipitation, snow, and midwinter and summer season temperatures. After choosing the position of the plant, some verification must be performed in terms of archaeological, architectural, historical, and landscape constraints. If there is presence of the critical infrastructures, or if there are buffer zones to be respected as roads, highways, railways, cemeteries, etc. In these slides are presented two different maps, which in the first one are shown the punctual restrictions for Liguria region. Instead, in the second ones are presented the buffer zones for Piedmont region. Now, after having chosen the position and verified the compliance with the regulatory context, it is possible to roughly estimate the endogenous potential of photovoltaic plant based on its geographical position by referring to maps or tables of the solar radiation, scientific papers, or by using different calculation softwares such as QGIS, PVCs, or PVKs. In order to understand the energy balance between the electric energy need and the energy produced by the PV plant, it's necessary to define the consumption profiles that can be done by data acquisition from energy smart meters, energy audits, or for Italy by referring to the National Statistic Center ARERA, which gives hourly consumption for residential buildings in Italy, or referring to the electricity bills in which the energy consumption is divided in different day slots, and we can summarize the energy consumed during the day and the one consumed during night. From now on, we'll deal with the PV plant design phase. First, it is necessary to define the installed peak power given the number of the panels and the panel peak power. At this point, a 2D drawing of the available surface, including the shape, orientation, buffer zones, and a panel technical datasheet must be used. Then, considering the minimum interval space, the 2D or 3D placement of the panels can be done by counting the number of the panels that fit into the available area and multiplying by the panel peak power that we take from the technical data sheet of the panel. The installed peak power of the panel can be defined, but we still don't know the producibility of the plant. At this point, to define the PV plant, to define the producibility of the PV plant, the PVSys version 7.4 is used here. The image on the left represents the first interface of the software. On the right side are given all the data that we must add to the software, divided into the main and optional parameters such as orientation, system components, detailed losses, self-consumption, near and horizontal shading, etc. Firstly, the positioning of the plant must be specified. Then the software allows to choose the closest meteorological station that provides the latest weather data file containing information about the solar radiation, temperature, the wind, velocity, and the precipitation. If we have more recent data, we can upload directly the file inside the software. Then it is necessary to define the orientation of the tilt angle of the panels. We can choose one for the entire system or different for each string. For estimation, we can refer to different scientific papers or calculators based on the geographical location, and start playing with the software until the losses with respect to the optimum are as low as possible. In order to complete the data for the PV panel plant components, two scenarios can be followed. The first one consists in preliminary sizing. So as we did before, we can directly add the plant power calculated inside the software, or we can put the available surface. Instead, the second scenario consists in no sizing, so we directly start choosing the PV model and adding their number, then defining the other components of the system as optimizers, inverters, array design with modules and strings. Then particular attention need to be paid to define the losses, as they can decrease the plant total energy production up to 15%. The horizon shading depends on the topography of the area, so it is more relevant for mountain areas. It can be defined by importing the 3D topography inside the software, but the PVC's software doesn't allow that. So we can directly use Google Earth Pro and extract in some elevation profiles to define the height in degrees for each altitude. Near shading can be caused by nearby building or vegetation, and in this case, to allow the other partners to work correctly, it is suggested to install optimizers. Near shading can also be provided by panels themselves, so we must pay attention and we should avoid this kind of shading by a correct definition of the interval space. The results are given in the results of the design can be given in terms of normalized production and loss factor, in incident energy to the panel, array power, and a loss diagram, which present the total amount of the energy produced by the plant, extract all the losses previously calculated, and presents the useful energy. If we provide to the software some information about the energy need, and if we add to the system some batteries, the loss diagram will be a bit different from the previous one, defining the useful energy produced, dividing the useful energy produced into direct use, stored energy, and energy fed into the grid. Moreover, the software provides also an evaluation of the carbon dioxide emissions balance, considering the saved CO2 emissions and the CO2 emitted from the production of the PV plant components. So further steps of the design phase consist in a detailed electrical design and generation of the electrical scheme, evaluation of the possible nature-based solution integrated with the PV plant and albedo modification inside the software, verification of the roof design capacity or the terrain consistency, choice of the supporting element that we have to pay attention if we are going to add too much weight to the roof, or if we can cause possible infiltration, performing an economic evaluation and the payback evaluation of the payback period. Uh, Energy service manager or energy service provider practice. Communication of the project to the municipality can lead also in further requirements as fire protection controls or safety regulation for the work execution on the rooftops, and a thorough examination of the legal and tax aspects. Referring to the grid-connected plans, the norm indicates some mandatory requirements, such as the required voltage for the energy fed into the grid and the use of the protection devices to prevent faults or fires. The project must be communicated to the energy distributor of the zone. The PV plant must be correctly installed according to the project design and then performed the commissioning of the plant. The real-time monitoring and digitalization allow to check the functionality of the plant, its producibility, and to make some possible adjustments of the energy consumption based on the production. Maintenance or cleaning, which depends on the typography of the area and the climatic conditions, is a key element that, if it is not performed when necessary, can lead to a complete cessation of the energy production from the plant. So thank you for your attention, and for more information in the knowledge sharing platform, please scan the QR code in the right side